And then there were some typos, and then somebody else fixed it, like what another typo.
Yes, which one?
Okay, let's get started, everyone. So today will be the last topic that could be a source of questions on your exam. So today we will be talking about broadly memorization versus generalization. And we will also be talking about factuality and hallucinations in language models. So both of these topics are very related to each other, right? So if your model is hallucinating, making up stuff that is not true, then it likely has not memorized whatever that fact is strongly enough within its parameters to be able to use that fact in multiple different responses. So, these topics are kind of hard to research because teasing apart what the model has memorized and even going further to localizing where exactly in this giant transformer did the model memorize this fact, that is a really hard problem. Like most facts are not easily localized to one or some small group of neurons that are in the same layer, but rather they're distributed throughout this giant transformer model. So it becomes very hard to figure out, what does the model actually know? And so I think this is like one of the most important problems that language model developers have been focusing on when they're training their next models. We see bigger and bigger models that are trained on more and more data. And one of the goals of training on that much data is so that the model can pick up as many facts as it can about the world and also pick up patterns that allow it to generalize to solving new tasks. Okay, so before I do that, I should also comment on the projects. So the project report template will be released tonight, and you can use it for writing up your report. It'll be 8 pages in the same template as the proposal was. And there's obviously other sections there that we'd like you to fill out. But something that is important to note is that you don't have to get like some really high accuracy or solve the task that you set out to solve in your proposal. Most of your projects will likely not work, or they will be, they'll work to some extent on some tasks and fail on others. That's totally fine. We're not grading you based on your performance. We do want to see that you've put in a lot of effort into the project. So if you wanted to, solve some task or hit some performance on a subtask, but you weren't able to, we want to know exactly what you tried and why you think that you weren't able to succeed. And so, just because you weren't able to succeed, that doesn't matter. But we want you to show us that you spent enough time and effort to kind of understand why. And, in many cases, it could be something like, well, we didn't have enough GPUs to actually scale this thing up, and that's why our model didn't work or something like that. But in other cases, we do want you to list out what you tried so we can kind of judge how much effort you put into the project. Does that make sense? Yeah.
I know last class you mentioned the code base, submitting the code base separately in addition to whatever paper we submit. Would a Google Colab link be good?
Yeah, a collab link would be good. GitHub public link would be good. We definitely prefer if you put your code into some public publicly accessible link and then just share the link as part of your report. That said, if it's easier for you for whatever reason to just send us a zip file of the code, you can do that. But yeah, we prefer any sort of publicly accessible link. Other questions? Okay, so let's start with memorization versus generalization. So here, we should make some kinds of distinctions. So memorization generally refers to sample or example specific information. So like one example that is easy to understand is if you take a math problem, right? So let's say 2 plus 7 equals blank. Now, there are multiple ways a model could reach the correct answer, right? It could, in its pre-training data, have observed the same math problem, tens of thousands of times. And so if it's able to encode that knowledge that 9 is the correct answer into its parameters, it could just simply retrieve that and say that that's the output, right? So in doing so, it would have memorized the answer to 2 plus 7, the math problem. It doesn't actually use the algorithm of addition or anything more complicated, like a general purpose solution that could allow it to solve many other addition problems. The alternative is that the model sees many instances of addition in its pre-training data set. So not just 2 plus 7, but 317 plus 27.5 and all these sorts of things. And there's just too much for the model to memorize. So something that we will talk about later today and formalize is this notion of the memorization capacity of a model. So each model, based on how big it is and how much data you train it on, has some capacity where after you give it more tokens than that capacity, it stops being able to memorize subsequent tokens. And so one of the kind of driving concepts behind this memorization versus generalization trade-off is that if you have a really big model, you need to train it on enough tokens such that it surpasses the memorization capacity of that model. If you train it on tokens that are like too few tokens, the model can simply memorize the entire training data set into its parameters, and it exhibits no generalization. If you train it on like trillions of tokens, the model cannot actually generalize to, cannot memorize the entire training set, and it's forced to start learning more abstract rules and concepts in order to lower the training data loss. And so, teasing apart what exactly is the memorization capacity of this model is important to determine like how much data do we actually need to train this thing on. All right, so we'll get to the factuality stuff later, but if you think about it, so just for completeness, the generalization part here refers mainly to like distribution level knowledge or rules. So instead of memorizing 2 plus 7 equals 9, a generalization of addition would allow the model to understand the overall process of addition so that it could work on any input. Okay, so one of the readings for today, which I'm sure all of you dutifully read, was how much do language models memorize? And so this is a paper by Morris et al. Done at Meta. And so their goal was to separate this memorization and generalization. And the key insight here is that like if you imagine I just train a model on internet data, it's kind of hard to separate memorization versus generalization because a lot of the next token predictions could be a product of either memorization or generalization, like 2 plus 7 equals, right? So in this paper, they construct a data set where generalization just cannot work. There's no way to generalize to do better than just memorizing the data set. So in particular, they quantify memorization by training a language model on random strings. So instead of English, here they just pick a vocab size, generate strings by randomly sampling characters from that vocabulary until they hit a particular sequence length. And so that's their training data set. Why is generalization not useful if you train a model on this data set, just so we're clear? Yeah.
Are there like no rules to generalization?
Yeah, there's no rules that it can learn about this data, right? It can't learn the process of addition because everything is just randomly constructed. There's no logic to the data set, right? So essentially, we have no generalization possible. And additionally, any performance better than random selection of characters shows that the model has memorized something about the training data set, right? So if I give it a training example and the model is able to regurgitate like the next token of that training example given a prefix, that indicates that this model has to some degree memorized that particular example. Again, there's no form of generalization that is possible here. So let's go back and kind of look at our, our cross entropy loss, our perplexity, and kind of formalize how we can measure this. So our model, let's call it theta, gives us the next token distribution, right? So probability of xi given all of the tokens before I. And we looked at the cross entropy loss as the average over all tokens in some data set. So let's say that's T. And here we'll just write it out for a single sequence. So we'll go from I to T. We take the sum of the negative log probabilities of all of the tokens in this data set. So this part here, the negative log probability of the next token given all previous tokens, we can also interpret as the surprisal. So, given this prefix, how surprising is the next token? And so if the probability here is low, right, of the ground truth next word, the model is probably more surprised at it compared to when the probability is very, very high and the model is certain about the next word. So this is pretty similar to our intuition about perplexity as well. So just to write this out, high probability gives you a low cross entropy loss, right? Because we're looking at the negative log probability. And we can also interpret this low cross entropy loss as the model requires fewer bits to encode this token. So we'll get back to this in a second, because we want to make a kind of connection between the probability of the model, the probability that the model assigns to the next token, and how much storage it would take to for the model to represent that next token. And the idea is that the less confident the model is in the next token, the more bits it would take to communicate that next token to someone else who has access to this model. So we're not going to go into all of the details around like arithmetic coding and things like that, but intuitively it should make sense. So here we have a high cross entropy loss when the probability of the next token is low, and this indicates that we need more bits per token to encode. Okay, so again, like the way in which we can convert this distribution of next words into kind of sequence of information that we can transmit is called arithmetic coding. There are many ways to do this, but the high-level intuition is that the lower the probability, the more bits you will need to transmit this information to someone else who has access to this language model. So when we have a full data set here, this term, which is the sum of all of the token level probabilities, and again, when we are training a language model, we're looking at the average token level negative log probability. But if we just take the sum, we can interpret this as the bits needed to encode full data set, which has T tokens. And one thing to note about arithmetic coding is that if you have a token with probability of P, it takes negative log base 2 P bits to encode this token. So if you're interested in the actual details of this, you can look up arithmetic coding, Huffman coding, things like that. But for the purpose of this lecture, we're just going to stick with the intuition here. Okay, so using the cross entropy loss, all of this allows us to estimate how many bits we would need to encode the full training data set, right? And so this number is a function of the probabilities that the model assigns to each of the next words in this training data set after the training process has been completed. Now, we want to measure how much the model has memorized. And the way we're going to do that is compare this quantity here. Sorry, let me just make some more room to make this readable. So we're going to compare this quantity here to the number of bits that you would expect the data distribution, like here it's completely random, right? So if the model had not memorized anything and we just know how the data was generated, how many bits would it take to encode this data set compared to this model that has been trained over the data set? So let's take a look at that reference number first, and then we can work our way back to this comparison and measure the memorization. So if our data is random, right? We have these random strings. Let's just, make some definitions here. Vocab is V. Let's say we have N sequences. S is the max sequence length. So we have N sequences, each one of length S, and each sequence is a bunch of random strings drawn from this vocabulary. And so each token is sampled uniformly at random from the vocabulary. So in other words, the data distribution here is the probability of xi equaling some word in the vocabulary given all previous words in the sequence is 1 over v for all words in, this should be the size of v, for all words in the vocabulary, right? So this is the true distribution of the data. There's no way you can, get a model to do better than this. This is how the data was generated. Does that make sense? So this is the setup. We create a data set that is constructed in this way, and we train a language model on this data set. So now we want a way to compare this number up here, which is the cross entropy of our language model trained on this data set, to a version where the model had not done any memorization at all. So let's compute that reference number first, and then we can subtract the cross entropy of the model from this reference to measure the bits of memorization from the language model. So, one thing to note is that, coming back to this cross entropy, we recall that this reduced to the negative log likelihood of the correct next word because our target distribution puts 100% of the probability on the correct next word and 0 everywhere else. But in actuality, the cross entropy loss, the general formula allows you to have a non-one-hot target distribution, right? And so this is, that was really bad. The sum over all of the words in the vocabulary, the probability of V times the log probability of producing V. So again, like in our language modeling case, this P of V is 1 for the correct next word and 0 everywhere else. So this reduces to the negative log likelihood. But in this case, that's not true, right? Because every word has a probability 1 over V to be generated. So if we write this out with our our data distribution here, that is 1 over the size of V times log of 1 over V. Since every word here has equal probability to be generated. And this thing just simplifies to the log of V, so the magnitude of V. So essentially, the entropy of our data distribution equals the number of samples, right? The number of sequences times the sequence length times log V. And so in this paper, they set V to 2,048 different word types, and so they trained their model over the same data set as well. So now we have an expression for the number of bits required to encode the data with the data distribution, and we also have the bits needed to encode this data set with our language model, right? And so to measure memorization, what we want to do is essentially take the difference of these two things. So let's do that. So if we're interested in this question, how much did our model theta memorize? We can define this quantity mem, which is just the difference between these two things. So ns log v minus, and then I'm just going to copy this thing from up here, this whole thing over here, which comes from the language model. All right, great. So just to make it very clear, this part comes from the data. So this is like the best you can do with our data distribution. And this part comes from the model that we've trained on the data set. And the difference tells us how much the model has memorized. So if we train this language model and it decided that all of the next word probabilities should be 1 over v, right, which is the same as the data distribution, then the memorization term would be 0, right? This difference would be 0, and that indicates that there's no memorization at all. And so if we trained a unigram model on this data set, right, we might see this. The model would simply just learn the frequencies of the characters in the data set, which would be the same if the data set is big enough as the true data distribution, and the memorization of that model would be 0. However, we don't have a unigram model, right? We have a giant transformer model that's been trained on this data set, and so that makes things more complicated, right? If you train this model over the data set, you're likely going to get a case where this memorization quantity is a lot greater than 0, which indicates that the models, the number of bits required to store the data set under the model is much less than the true data distribution. So this indicates model is memorizing. Okay, so any questions about this? The intuition, at least, should be clear. Yeah?
In the part that you say that it needs more bits, aren't we then like sampling from the distribution of the next probable word?
So in this case, we are not actually generating any sequences from our model. We're just looking at the probability distributions, right? So the cross entropy loss is computed using the distribution, right? The next token distribution, yeah. But this does relate to your question that if the model has memorized the data set, then if you gave it a prefix of a training example, you would expect it to be more likely to regurgitate the rest of that training example than like a unigram model that has no capability to do so. So those two things are very related to each other. Yeah?
How do you balance like not getting memorization but still being good at like retrieval if you do want like a definition of something?
So your question is balancing this regurgitation of the training data with what exactly? Like generalization or?
Like being able to retrieve something to give information on.
Okay, so I guess what you're talking about is there are some kind of good uses of memorization, right? Where retrieval of facts and then using them.
Yeah, for like a definition of something.
That's a great question. So that is like, there's no answer to your question, unfortunately. like the model kind of learns how to do this, but we also see unintended consequences of memorization as well. Of course, if we could like tease those apart, we might be able to like post-train the model to get rid of those unintended impacts. However, we have no idea essentially where memorization occurs, how it occurs, and it like functionally within the transformer. So it's still an open question. Like if we remove all memorization from the model, it's going to be bad at so many different tasks, right? So yeah, the way we set this up and all these research papers set it up is this tension between memorization and generalization, but both of them are very linked to each other as well, which makes it hard. Yeah.
For the cost entropy general formula, does the PV term, is that either 1 or 0 when it comes to language models? Is that what you were saying earlier?
Yeah, so because when we're measuring the cross entropy of our language model, we're looking at the correct next token, the probability that the model assigns to that, right? In this case, the data distribution, this is how we created that data in the first place. And so this is the underlying true distribution. Yeah.
Okay. So then would that be like, could you explain like the 1 over like absolute value of v part when it simplifies?
Sorry, you mean
Here. Like in the general case.
up here?
No, in the general case, sorry.
Oh, in the general case. Oh, over here?
Yeah.
Yeah, you can work. I skip like 5 or 6 steps here, just because it didn't matter. But yeah, you can work it out yourself.
But it'll end up with log v.
Yeah, the whole thing you'll end up with log v. Yeah. It could be the exact same if the, so note here that first of all, this t up here is equal to n times s, right? It's the total number of tokens in your data set. And if the model assigns a probability of 1 over vocab size to every next word, regardless of the prefix, then you get the exact same term here compared to the. Yeah. So it is the number of examples times the sequence length. Yeah, I should have made that clear. That is. Yeah, I mean, okay, so this is a simplification. What this should be is a sum over all of the examples as well as a sum over the sequences. So I could write that maybe actually, although the indices will get annoying. Maybe I'll just write sum over all examples and tokens. Yeah. Okay, so now let's take a look at how this memorization term is actually behaves with different model sizes. Yeah. Yeah, so in this specific case, the model is, the data distribution is completely random, right? And so if you used this data generation process, this is the best you could do on any test data, right? However, our model is going to be trained on the training data set. So like optimally, it would learn this data distribution, but of course it will never do that because it doesn't have like infinite data, and there's no way for it to get back the exact data distribution. So it's always going to be an imperfect. And we'll talk later about how this looks on actual text, where the data distribution is not random, right? There's pattern, grammar, and all the things we know about natural language that void this this assumption. The problem is we don't know what the true distribution is for text, right? So this is just a highly synthetic setting that allows us to make some sort of measurements. Okay, so I guess a lot of these, yeah.
Isn't memorization going to happen no matter what? Like, what are we trying to measure here?
Yes, memorization is going to happen no matter what. We are trying to measure how much the model memorizes. Yeah, it's always going to be non-zero, but in certain settings it could be higher, and in other settings it could be lower, as we will see in the paper. So,
is there like an issue with like a different amounts of memorization?
yes. So if the model exhibits very high memorization, like the entire training set has been memorized, this may mean that the model cannot generalize
Right.
to. So it's related to like overfitting, right, as well. Yeah. Do you have a question?
Probably not a question. Like how large should how large above zero should be considered like a problematic?
Yeah. So this depends on the setup of the data, right? So how many word types are in the vocab, how many examples are in the data, and so on. So we will see in the the paper plots. Yeah.
So how does this like fit into like whether we're memorizing the training data? Like how does, I mean, this is just like a very synthetic like pool of.
Yeah. So this is purely for just getting an idea of how these transformer models behave when we know the data distribution.
Okay.
And the paper will try and connect this to how they behave on natural language, but with a lot of disclaimers. Like obviously, real pre-training data does not look like this. There's a lot of duplicates in the training data, which might be easier for the model to memorize if it sees the same thing over and over again. That's not taken into account here. And there's also grammar and other rules. So it's a very toy setting, but it's still useful kind of in the theoretical sense to get an idea of like how many bits per parameter can the model memorize in theory.
Yeah, but is the size of this like based off of the size of the training data set?
The size of the model?
Like the what's it called? The vocabulary and stuff that we are using for in the synthetic data.
Is it based off the training data size?
Yeah.
So these are just hyperparameters that
Okay.
they selected. There's no reason to select different ones. But yeah, it is interesting to see how it would behave with different vocab sizes. I think it's just like so many experiments for them
Yeah.
because each setting they have to train a bunch of different language models on this synthetic data, which I'm sure Meta was like, wow, we're wasting our GPUs on training on this garbage data. But I mean, the end result is pretty interesting. Okay, so let me get to the end result.
Okay.
So that might make it clear why we're talking about this. Okay, so let's assume a fixed model size. So let's say our language model has like 1 billion parameters in it, right? We already talked about how to set the parameters of our transformer by increasing number of layers, dimensionality of the model, etc. So we're going to keep that fixed. And on this synthetic data, the memorization, this difference between the data distribution and the model distribution in cross entropy, increases as the data size, so the number of tokens, increases, but then plateaus. So at some point, as you give the model larger and larger data sets of random tokens, it seems like the model is not able to memorize any more information. And so we see this plateau in this memorization term. And so what they do is they measure this, like where this plateau occurs, and they call it the capacity. So the capacity, we can call it C, of model theta is the max value of this mem term over the increasing data size. So they keep increasing the data size until they observe the model plateau, and then they look at what is the max value of this memorization term as a function of the data size. And then they do one final tweak to this capacity where they want to measure the number of bits per parameter that the model can encode when it's hit its capacity. So that is simply this C of theta over the number of parameters in the model that you're training. And the last thing I want to say about this paper is that empirically, so they train empirically, they train a bunch of different models of different sizes over a bunch of different synthetic data sets of different sizes, like numbers of examples. And they find that across all of these models, if you plot, we find a kind of uniform capacity across all of these things, which is roughly 3.6 bits per parameter. So a model can memorize roughly 3.6 bits per parameter, and this is very helpful because if you have a model that's like 8 billion parameters, you can then use this estimate to figure out how much data can this model actually memorize at max capacity. Obviously, with all these caveats that this number was found on synthetic random data and not on natural language, and we don't know how that influences the capacity. But at the very least, it serves as some sort of lower bound of because this is like the hardest kind of data to memorize. There's no way to generalize here, if that makes sense. And then the other thing that the paper finds, which is also very interesting, is on text data, once the, on non-random natural language data, like you would find on the internet, once the model capacity is exceeded, the model starts to generalize. And so one consequence of this is that if you train a big model on a small data set, and that data set is lower than the capacity limit, then you will observe that the model memorizes a lot more than if you trained it on much more data. And intuitively, this also makes sense, right? The model has a finite number of parameters, and if you just keep giving it trillions and trillions of tokens, at some point it runs out of storage space to memorize those exact tokens. And so it has to do some sort of compression, and the compression process results in generalization. Okay, so let's take a look at some examples on from the paper now that we've kind of gone through how these plots, how the capacity works. And first, you can see here models in the GPT family. So they do all these experiments on like GPT-2 sized models from 500K, which is tiny, to 1.5 billion parameters. 1.5B is still pretty small by today's standards, but that's another kind of limitation of the paper, is we're not sure how this might generalize to like 2 orders of magnitude bigger models. Okay, so let's look at this first plot here. On the left, we see the memorization, that mem quantity that we just talked about on the synthetic random data set here. And so you can see that the x-axis is the size of the training set, the number of examples, and the different colors here are different sized models. So you can see this yellow model, which is the largest of these models. You can see the memorization component goes up as the training size increases, but then it plateaus, right? And we see a lower plateau with all of the smaller models. And you can see that as the model gets smaller, the plateau effect starts sooner, right, with fewer tokens, which suggests that each of these smaller models has a lower capacity than that of the larger model. Now, the interesting thing is that the right experiment is training models on real text data, not this fake random data. And instead of observing these plateaus once the capacity is hit, we actually observe that the memorization decreases as the number of data points gets larger and larger. So on the random data set, we see that the memorization plateaus, but on text data, we see that it sharply decreases. So why might this be the case? Any ideas? Yeah.
Story to generalize.
Yeah, exactly. So on natural language, there actually is a way for the model to generalize and learn these higher level processes in order to figure out what the next word is without just rote memorization, right? But on the synthetic data set, there's no other strategy that it can use. So it can't do better. We just see that it's memorized all that it can, and it just doesn't improve on the remaining tokens. So this is, yeah.
So if they generalize, the memorization bits goes down always?
What's that?
So if they generalize, the memorization bits always goes down?
Yeah, so let's look at another plot that'll make this more clear. So this plot, I think, is the most useful one. So here, the y-axis is the test loss. So now we're looking at tokens that were not included during training. And the x-axis is the ratio between the data set size and the capacity, like the max memorization capacity of the model. So we see here that the test loss sharply increases until the model capacity is reached. So let's interpret that, right? The test loss is a measure of generalization, right? The lower the test loss, the more the model is able to generalize from the training set to the test set. So we see that the test loss increases by an entire order of magnitude when it hits this capacity limit, which means at this point, the model is not at all generalizing to the test set. However, it's doing pretty well on the training set by virtue of having just memorized all of the tokens it's seen till that point. Now, you see that as the number of tokens in the data set gets larger and larger, right, and goes beyond the capacity of the model, we see the test loss also start to drop, which indicates that the model is actually generalizing to the data set. It's not simply memorizing. And so this side of the plot over here shows that the model eventually reaches a much lower test loss by doing something more than memorization. So this plot is kind of the coolest one in this paper because it shows that the point where the test loss peaks is right when the training data size equals the memorization capacity of the model. Does that make sense? Yeah.
So basically, we're saying that at first the model only memorizes, and then it starts to generalize.
Yeah. So that is a good way to interpret these plots. I mean, I would be careful of saying the model only memorizes, but clearly early on during training, the model is primarily memorizing because it hasn't been able to learn any of those rules. And it's only as it sees more and more examples and it cannot possibly memorize that it starts this generalization process. So this phenomenon has also been observed in other machine learning settings. You might see the term grokking, which has been kind of popular in machine learning. It refers to kind of the same thing where the model first overfits the data set and then exhibits decreased test loss after further training. There's also this concept of double descent that is kind of paralleled in these cases. So yeah, these are kind of important concepts to understand when it comes to how does a model behave during the training process. Like, it starts out by memorizing all that it sees, and then once it hits this capacity limit, it then starts to actually generalize. And the latter is what we kind of want when we have a general purpose like chatbot that we want to be able to answer arbitrary queries. Yeah.
So why are all the model sizes so small?
Because
Is this paper from a while ago, or?
no, this is from this year. The thing is that, like,
Too.
yeah, it's very expensive because for each model size you need to train a ton of different models with different training data sizes and so on. The first author of this paper is also an intern, so he's not going to get all of the cluster to do these experiments. But yeah, okay, so clearly we can see that the model is capable of memorizing. And now let's kind of transition in the last 15 minutes to talk about in the natural language setting, which is way more complicated than this random string setting, how do we measure which facts the model has chosen to memorize and how it generates those facts in response to different user queries. So we'll shift more into kind of a real world practical scenario instead of this more theoretical one. So let me go back here. Okay, so now let's talk about factuality. And the general setting we're interested in is a model gets a prompt X, generates a response Y. How factually correct is Y? So this is like the most generic statement of the task. You could imagine a simpler form of this where your prompt is like a very specific question. What is the capital of Maryland? And the model produces a single word as a response, and then it's very easy to measure the accuracy of that model, right? And there's many data sets that do this. However, that is a highly simplified version of all of the use cases of ChatGPT. Ideally, you would have any possible prompt that can be put into the language model and any possible response. It could be, multiple sentences, multiple paragraphs, and regardless of what the model response is, we want some way to measure the factuality of that response. This is a lot better because now you can actually measure how the decoding time hyperparameters like the sampling versus greedy decoding, the temperature, all of those things affect the factuality of the resulting response. Okay, so the dominant approach to measuring factuality is to take the response Y and break it down into a list of factual claims that are made in that response. So there's this pipeline where we first do decomposition of Y into a list of claims, and then verification of each claim against some reference knowledge base or knowledge source like Wikipedia or Google search or something. And then finally, aggregation of, so we want to compute percentage of claims that are supported by evidence. So this pipeline is kind of the standard one that people have been using. It actually was proposed by a paper that I worked on with one of my PhD students a couple years ago called Fact Score, which did both the decomposition and the verification stage with two different language models that were trained for this specific task. This was like back in like 2023, so now things have improved a lot. And the verification stage nowadays is generally done by taking a claim, feeding it into Google search, or now even something like deep research, and gathering as much relevant evidence as you can before determining if the claim is accurate or not. So I want to quickly show a figure from this paper to explain how this works. So here we see this response. This is just a snippet. So Bridget Moynihan is an American actress, model, and producer, best known for her roles in Grey's Anatomy, iRobot, and Blue Bloods. She studied acting at the blah, blah, blah. And so the task here was write a biography of this actress, and ChatGPT produced this. In the decomposition stage, we break this response into a giant list of all of the claims that are made about this person. And then in the verification stage, we send each of these claims to a language model with some relevant evidence. So in this paper, it came from Wikipedia, but in general, it could come from Google or deep research or whatever. And that model would take a claim like Bridget Moynihan is a producer and match it up against her Wikipedia article to see if she actually was a producer or not. So if that was not mentioned in her Wikipedia article, then it would return unsupported. Otherwise, it would say it's supported. So in fact, she was never in Grey's Anatomy, although ChatGPT thought she was. And so you can finally aggregate all of these scores at the claim level to get a single score for a response, and then you can further aggregate all response level scores to get a model level score. And then you can rank, all of the LLMs by this fact score. So, this is something that we can measure on any language model. And the scores are far below human performance, at least in 2023. Nowadays, the models have gotten a lot better, but they still make a lot of factual errors. And so what are some reasons that a model may say something like she is best known for her roles in Grey's Anatomy, even though that's not true and did not occur in any of the training data examples probably that the model saw? Like, what are some plausible reasons for this hallucination?
There's an actress with a similar name that plays in Grey's Anatomy.
I don't know if that's true or not. I mean, theoretically, there could have been some actress in the general case with a similar name in Grey's Anatomy. It doesn't even matter if there was a similar named actress, right? There was some actress in Grey's Anatomy, and some element of that prompt probably encouraged the model to put high probability in all actresses that appeared in TV shows, and maybe it sampled one of those incorrectly, right? What are some other reasons why a model could hallucinate like this? So let me ask it a different way. Is it possible to completely get rid of hallucination in a language model?
No.
No, why not?
Because every time you are sampling from the distribution, so if you are doing that, then there's always a chance that use a low probability prediction.
True. Okay, that's fair. What if you're always using greedy decoding from the language model? Can you get rid of hallucination? Well, okay, let's say you don't have access to any tools. You just have a pre-trained model. Can you remove all hallucination?
I mean, the LLM does not have enough memorization capacity to memorize literally every fact that exists. So
Yes.
There definitely will be something wrong, even if the generalization is not 100% perfect all the time.
Exactly. There's no real way to generalize to this fact, right? Like, there's no strategy I could take other than just knowing that this person acted in this show. So, because a model has a finite memorization capacity, unless it has, like infinite parameters or enough parameters to memorize the entire training data set, it's simply not going to be able to memorize every possible fact about the world that's in the pre-training set. So another thing that I want to highlight here is that, oh, yeah.
So the fact here is coming from the Wikipedia, and I'm modeling for if I give a prompt that I develop a fact, such as I ask the model to do some
Yeah.
classification, such as A or B or C, and the model I do this like thousand times to the model, and the model gives like D, E, which is not in my prompt.
Mm-hmm.
So that's kind of like is that also hallucination?
Yeah, okay, that's a good point. So if you look at like research into hallucinations, they categorize different kinds of hallucinations. So this is like a factual hallucination, something that is true about the world but is false in the output here. But there's also like, if the model didn't follow your instruction to only output like A, B, or C, and it outputted D, that's also kind of hallucination in a way. Like you could define it as a poor instruction following or something like that, but it made a choice that is outside of the acceptable options that you laid out in your prompt. So it kind of depends on the type of research that you're looking at. Okay, so one other thing I wanted to mention is that ideally we could cut down on hallucination if the model were aware of what it had memorized and what it didn't, right? Because there's actually a simple way to avoid any hallucination in a model. It could just output I don't know for every prompt, right? There's no hallucination there because it never actually generated any fact. It just refused to answer every prompt, right? So this is like a perfect model, no hallucination at all, but it's also completely useless. So like most of the research now is trying to find a balance between this extreme case of a model refusing on all tasks and a model that tries to perform every task even if it doesn't have the knowledge encoded in its parameters, right? The problem is we don't know what the model has and hasn't memorized. There are ways to kind of probe the knowledge, like what is the capital of Maryland? If the model answers correctly, that likely means the model has encoded that knowledge somewhere to some extent. It doesn't necessarily mean the model can use that information appropriately in all contexts. So that makes it a little harder to tell if the fact has been completely memorized or not. But yeah, this also relates to this area of research on abstaining. So how do you determine if the model should say, I don't know, or maybe the model should learn, well, I don't actually know what roles this actress, what TV show she acted in, so I shouldn't output anything about her roles in TV shows. I could say, I don't know what roles she played in, right? We still have no techniques for doing this. And so, we can try and RL our model so that when they output very, responses that are not factual, we can train them to instead say, I don't know anything about this. But that's kind of a reactive measure. It's kind of like patching all of the things that we observe the model doesn't know anything about, rather than the model itself kind of being aware of what it knows and doesn't know, which is, still open area of research. You could imagine I could just look at the probability of the next token, and maybe the probability of Grey's Anatomy here is extremely low, but higher than the probability of other TV shows. Versus if the probability of Grey's Anatomy were like 100%, maybe we could determine that the model is confident enough that it has memorized this fact and it knows it. But a lot of research has shown that model confidence is not a reliable predictor of if the model has memorized things or not. In fact, it can be very overconfident in things that are just wrong. Like it might assign 99% probability to Grey's Anatomy here, even if it's false. So, nothing is perfect here. All models still hallucinate, and hallucination rates have dropped a lot between 2023, when this paper was written, and now. So we can look at even like the plot in this paper. So this is the fact score of all of these models. At this time, GPT-4 was the best model. So we see it has a fact score of like 75% or so, meaning 25% of the time the claims that it produces are just wrong, or they're unsupported, compared to humans that are close to 95% or higher. Now the hallucination rates for models have dropped a lot, so they're much closer to human performance. But still, like, you would like the model to abstain when it doesn't know something, and that is not happening yet. So open area for research here. Okay, any questions about factuality? Yeah.
Is this data based on without like any tool calls or anything?
Yeah, their tool calls like didn't exist at this time. So this is all like calling just the pre-trained model or post-trained model. I should also note that because fact score and all of the metrics like this give you a single number for a response, you can use it for reinforcement learning, right? You could just say, I want to maximize the fact score of my responses. Many people have tried to do this, but reward hacking is really strong here. So we find that if you optimize a model to increase the fact score does improve, but the response length also gets short. So the model just decides to output all of the obvious statements about the person that it has memorized, and gives you very incomplete biographies. Also, it seems to make the biographies non-chronological when you do reinforcement learning in this way. So instead of ordering a person's life by, they were born here, they went to school here, then they accomplished all of these things, now the model tends to order these statements by how confident it is in their factuality. So it might say, oh, this actress won an Oscar for this award, for this movie. She was born here. She won an award for this other movie. And so it's not coherent. So overall, reward hacking, still a huge deal, and just optimizing factuality with reinforcement learning is not a viable solution by itself. It needs to be paired with many other penalties for it to work. Okay, so we will do an exam review type thing on Monday. There's no other material that we will cover for the exam, new material. So, and I will post the final project template today. So see you all on Monday.
Will we get more examples?
No, those are all the, a lot of the content we covered in the second half is totally new, so there's no practice material.
Sorry, do you have a cheat sheet for the exam?
Yes, the same setup as the first exam. Yeah. Yes. One both sides.
Oh, no. It's not
Yeah.